Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today, it's my pleasure to welcome Shireen Aubert, the Dean of the Joint School for Nanoscience and Nanoengineering. To get us started, Shireen, can you tell us how you first got started in nanotechnology?
Thanks very much, Lisa, and thank you for the invitation to be part of Stories from the NNI podcast. I got involved in nanotechnology when I was a graduate student. I was very fortunate to have been in the lab of Professor Catherine Murphy, whose work has really pioneered the field. As a graduate student, Kathy gave me lots of flexibility to work on various projects in the lab. And although it was an inorganic lab at the time, we were very excited about the emergence of nanoscale science and nanotechnology. And our lab at the time started really looking at various types of nanoparticles and studying their optical properties and learning how size and shape could really manipulate their properties. And I was very focused at the time on developing sensors for various types of chemicals as well as biological agents, and was really excited to be able to use the optical properties of these nanoparticles as modes of signal transduction. So that was sort of my first introduction to nanotechnology. And I then went on to conduct a postdoctoral fellowship at the Johns Hopkins University, working in the lab of Jerry Meyer. While I was there, our work focused on developing systems for decontamination of environmental pollutants. And I became very interested in learning how we could develop different types of nanomaterials that would actually be used and assembled in ways by which we could get them to react with pollutants in ways that they could not do if they were not anchored onto other types of molecules. So this led to being able to amplify efficiency of the processes and really led us to discovering some really interesting work in the area of pollutant decontamination.
So you mentioned that you were developing sensors for detecting a wide variety of molecules, and some of those biological and perhaps others not. Could you talk a little bit more about the types of things that you could detect?
Absolutely, yeah. So my early work focused on the detection of lithium ions. We were very interested in understanding how lithium ions functioned in batteries and being able to measure the gradients and how they were transported. And lithium became even more interesting. As many people are aware, lithium is used as a drug for people who suffer from different types of neurological disorders. And so we started looking at how they function with respect to biological systems. And so that was sort of my early work in terms of detecting things. I then went on to start my career. And at the time, I was really interested in how do we build sensors for other types of things? And with a training as a graduate student, as well as a postdoctoral fellowships and things that mattered for the environment, and also a lot of my history in terms of growing up, I was very interested in environmental matters. I became very interested in looking at different types of environmental pollutants. And one of those was organophosphorus pesticides. So a lot of organophosphorus pesticides, you can literally walk into some home department stores and purchase them. And it turns out that there's a class of organophosphorus pesticides that are used. And when you look at their chemical structure, they're very similar to that of chemical warfare agents. By just changing one atom, you end up getting a pesticide. So people take these molecules and turn them into pesticides and spray them on agricultural lands. And there's a lot of reports out there that tell you when people are living in these environmental agricultural areas, they tend to develop some type of neurological disorder because they've been exposed to all these chemicals. And some studies have also shown how negative this impact is on young kids. And so at the time, I was sort of really interested in understanding how do we actually detect these? And so as you begin to really monitor what's going on agricultural farms, they spray a significant large amount of pesticides. And it turns out that only 5% is actually doing what it's supposed to do, and 95% remains in the environment. And so one needs to be able to detect them. They show up in milk, in meat, they show up on plants. And so being able to detect them and also distinguish between them is extremely important. And so we decided to begin to look at how do you actually detect them and how do you distinguish between them and how do you make sure that they're extremely sensitive and selective. In my lab, one of the things we started doing is looking at how to build these molecular sensors that were extremely sensitive, but attaching them to nanoparticles as ways to really amplify those signals. And we found not only was that methodology extremely effective in terms of detecting and distinguishing between the organophosphorus pesticide, but it allowed us to also eliminate false positives. So a lot of sensors are built with false positives, and it becomes really difficult to know whether you really have it or you don't have it. But by anchoring these nanoscale sensors, we were able to develop a system that had multiple modes of signal transduction. So an example was a system that gave you fluorescence spectroscopy as well as electrochemistry as one mode through the system. And so you turn on both of them to be able to detect, and based on the signals that you're getting, you know whether you have it or not. These systems were also extremely sensitive because of being able to attach them to these nanoscale materials. And they were also selective and reversible. So it offered us an opportunity to really look at what's in the environment. How do we know that they're there? How do we distinguish between them? And how do we reuse the sensor again? And it was really advantageous at the time because what people were doing is really going to an agricultural land, picking up a sample, bringing it to the lab. And when you do that, your sample can undergo decomposition, and the integrity of that sample is just not safe. So these sensors allowed us to be able to literally go into the field and make those measurements while we were there in real time and be able to really understand what was going on.
Based on your measurements, were you able to change the process or the application or the way pesticides are used in agriculture?
I think because our sensors were able to illuminate how widely spread they are, not only on the ground, but within the farm animals, I think that was an opportunity for people to realize not only is the way we're spraying them really concerning, but maybe we need to select different sensors that are not so toxic. And so there's a lot of work now being done in the area of looking at pesticides that are just less toxic to the farm animals and less toxic to the people that are doing the agricultural work. And I think that is extremely important. So one of the things we're excited about is the work that, sometimes we develop in the lab begins to help people realize the impact and hopefully change human behavior for the better.
So I want to switch gears and talk about the joint school and the really novel collaboration that came together to form the school and the facilities. Can you just talk a little bit about the institution?
Yes, and thank you for bringing that up. So, the Joint School is really a wonderful collaboration between two universities located in Greensboro, North Carolina. So, North Carolina Agricultural and Technical State University and the University of North Carolina at Greensboro. Both belong to the UNC system, but they're all independent from each other. The UNC system has 16 institutions of higher education, and they all operate independently. But this was really an opportunity to put together a shared facility that allowed education, training, research, and also opened doors for the facilities to also be open to companies that wanted to collaborate with the faculty that are here, or maybe startup companies that needed access to facilities that you only find in a nanofabrication facility. Founded in 2009, it has two departments, a Department of Nanoscience and a Department of Nanoengineering. And we have close to 150 graduate students. We only train graduate students. We don't have undergrads, even though we do have undergrads who will come and do research, and as well as high school students. We also do a nice collaboration with Forsyth Technical Community College. That is one of the few community colleges in the country that offers an associate's degree in nanotechnology. So the school has really offered an opportunity to bring scientists and engineers from different backgrounds, all with an interest in nanotechnology, to really live in this one location and to try to develop courses to educate our students, but also to conduct their own research. And what is really beautiful is to see how they really focus on big problems, and they use each other's training and background to be able to solve these problems together. It's a beautiful collaboration where they'll develop materials and maybe they're looking for an application somewhere else, and maybe another faculty member may have that expertise, and it comes together in a really beautiful fashion. So the areas that we've really focused on, broadly defined, has been in the area of advanced materials and looking at how nanotechnology can influence that. We also have a newly formed group that's focusing on some of the nanobiology or synthetic biology applications. And then we have a group that's really focused on computational simulations of nanoscale materials. So together, they really have addressed a lot of the areas to really strengthen collaborations and partnerships with other faculty from the two universities, but also collaborations with industry as well as government units. So that's one of the beauties of having this facility that really brings these people together. And as they do that, they start thinking broadly about the education of students and how students are always really excited about transferring the technology that they're developing. So we've also started a few certificate programs that are helping our students really think of entrepreneurship, but really not just any kind of entrepreneurship, really scientific entrepreneurship. So we want to make sure that our students are really thinking of technology transfer and intellectual property and commercializations and all the nuances in between. So that has been something that we're able to offer that is unique, and our students really find tremendous value in that. Because of the equipment that we have in the facility, we're also able to open it up to other companies to be able to come in. But not only do they want to use our facilities, they want to have some training. So we've started a certificate program in instrumentation where they're able to come in and learn about whether it's microscopy or how to operate the clean room or how to use a BSL-3 lab. So all that is now made easily available, and they don't have to be enrolled in the master's or doctoral program. It's much simpler to be able to take a few courses here and there and to get that certification that they need.
So I want to just talk a little bit about the instrumentation and the facilities aspect of the joint school. And as part of the National Nanotechnology Coordinated Infrastructure, I know that several of our podcast guests have talked about the role that access to instrumentation played in developing and expanding their companies. So can you talk about the network and the role that JSNN plays in the national network?
We are part of the National Nanotechnology Coordination Infrastructure through a site known as SENIC, which stands for the Southeastern Nanotechnology Infrastructure Corridor. And it is shared between the Georgia Institute of Technology, North Carolina Agricultural and Technical State University, and the University of North Carolina at Greensboro. Oftentimes, you'll find facilities that have instrumentation, but you really need expertise. You really need the right type of people able to, one, you just need to take care of the equipment and make sure it's consistently running. So maintaining it, servicing it, but having that expertise and knowledge on how to take different types of samples, from a biological sample to maybe a semiconductor type of material to maybe a biomaterial. You really need to be able to have that expertise on how to fine tune your instrument so that it gives you the right type of data, the precise type of data. And so the NNI has provided us with the resources that are needed in order for us to really equip the facility with the right type of technical expertise. And this has been something that I would just say is priceless. Having that in the facility is really priceless.
I want to get your thoughts on working across disciplines. When you were describing your own research, it seems like you'd have to have understanding of materials and chemistry and biology and environmental aspects. So from your own perspective as a researcher, but then also as dean of the Joint School, what are your thoughts on working across disciplines?
For many years, I remember when I was a graduate student, it was almost frowned upon, right? Like, as a chemist, I was expected to be the best chemist possible. And trying to work as a postdoc, I started working with environmental engineers, and I thought it was extremely critical. And the faculty that I worked with felt that it was critical, but you could tell it wasn't something that was celebrated very well. But over the years, I think with advances in the type of journals that are available, the interdisciplinarity that you see within the journals and the welcoming of these fields has really opened the door to encouraging more collaborations to happen. I think the funding agencies also pushing scientists to really focus on the interdisciplinarity. There's also been some restructuring within some federal agencies on how we think about doing good science and good engineering, and the encouragement of collaborations that has really pushed it. But as we have pushed it, I think scientists have felt comfortable working with other scientists. Engineers are feeling comfortable working with engineers. What's really fascinating for me here at the Joint School is to be able to bring the scientists and the engineers together and to get them to really think outside the box and to create what I feel is that converging discipline, right? So it's not just an integration of knowledge from the different disciplines, but it's really a unified intellectual framework, which I like to call the nanotechnology discipline. And so as we're doing this, we're seeing more and more encouragement. I mean, it was fascinating to see the National Science Foundation push out convergence calls as part of their big ideas. And I think that has really encouraged more people to work together. The part that I have enjoyed the most is not just getting the scientists and the engineers to work with each other, but to really get the economists and the social scientists to begin to have these conversations with our scientists and engineers, because it really forces us to really understand what the stakeholder is looking for, what the stakeholder needs, and to really go back into the fundamental science and be thoughtful about the needs of those people who are going to use the science and the technology, and to really frame it in a way that is going to be useful. It's also teaching us as faculty to be better listeners to who's going to benefit from the work that we are doing. So it's really transforming how we think about what we do in our labs, how we train our students to think. And it's getting people to be better trusting of what scientists are doing. And I think to me, that is really, really critical as we continue to move forward in making scientific advances.
Looking at both the past accomplishments in nanotechnology and opportunities for the future, how does that frame advice that you would give a student?
So the advice that I give our students is to really do everything possible for them to be strong critical thinkers, to really question what they're doing, to question what they're reading, to question what they hear, and to really be thoughtful about it and to utilize as much knowledge as possible to find answers to these questions is really, really critical. We really need our students to be thoughtful in terms of the work that they're doing, but to also be thoughtful in terms of being open to integrating knowledge that is acquired in different disciplines. That is so important as they begin to think about their contributions to science and technology, as well as when they go into the field, what they're going to be able to develop. It's important for them to also communicate clearly and being really open to other people's thoughts, whether it's something they agree with or not. I just think it's really important for them to learn how to listen and to draw their own conclusions.
I want to thank you again for taking the time to talk with us and just ask, do you have any closing thoughts that you'd like to share with our listeners?
I think it's so important to be able to lower those barriers of whether it's a discipline or whether it's an agency. One of the things that I have seen happen through the work that we are doing right now is the collaboration with scientists and engineers across different industries, with government agencies. And I really think that that's where the innovation lies and the transformation to really make the world a better place.